Hello everyone, welcome to the first streaming session for biology. I'm a biology tutor at the Learning Center, and today we'll be looking at an activity to understand more about the logic behind Hardy-Weinberg Theorem. This theorem describes how genetic alleles will be inherited from one generation to another, and we will also learn how to tell whether a population is evolving or not. So this is the worksheet that we will be going over. Let's first look at some important definitions that are central to understanding the Hardy-Weinberg theorem. The first one is population, which is an interbreeding group of individuals of the same species. Then a gene pool is all the alleles contained in the gametes of the individual in the population. Then a genetic drift is evolution, which is defined as the change in allele frequency. So this is what evolution is defined as. And so that evolution occurs in a small population. And that is as a result of chance events. So the next one is the Hardy-Weinberg Theorem. Oh, hi, Jeff. We just got started, and I'm just going over this worksheet if you want to follow along. So I just went through the definitions that are important for Hardy-Weinberg theorem, and that is population, gene pool, and genetic drift. Do you guys have any questions so far? Okay, I'm going to move on with the worksheet. So we're looking at the Hardy-Weinberg theorem, and it states that a population is not evolving, which means that the allele frequencies and genotypes remain constant from one generation to another. So if a population is not evolving, we can be sure that the frequencies and the genotype frequencies are remaining same from one generation to another. And that is what the Hardy-Weinberg theorem tells us. And there are certain assumptions that need to be true for the Hardy-Weinberg theorem to be true. And the first one is that there are no random allele frequency changes. And we need to be sure that there are no allele random frequency changes that can affect the gene that we're actually looking at. And then the second one is that we don't want a net migration of individuals either into or out of the population, and that there is no net mutation. Then mating needs to be random. This ensures that there is no preference for a certain gene and is not selected for more likely than another gene. And the last one is that there is no selection, and this ensures that the offspring from all possible mating are equally likely to survive. So these are the 5 assumptions for Hardy-Weinberg equilibrium, and it's important to understand and memorize these assumptions. Any questions so far? Okay, we'll move on to looking at the Hardy-Weinberg proof from a more mathematical and a statistical viewpoint. So this question is going to show why the Hardy-Weinberg equation is the way it is. So first, let's consider genes that only have two alleles. And the Hardy-Weinberg equation is used for genes that only have two alleles. So a big R, we're going to assume is dominant, and little r is going to be recessive. And the sum of total, the dominant allele and the recessive alleles are all alleles in the gene locus, or 100% of the alleles of that gene. So that gives us this relationship. And this says that the dominant plus the recessive gives us the total alleles for that gene. Oh, and it's also important to note that frequencies are usually stated as percentages, and their associate probabilities are given as decimal points. So if a question asks what is the frequency, you would give it in a percentage, but if it asks what are the probabilities, then make sure to give it in a decimal fraction. Okay, so if we assume that 50% of the alleles for the fur color in the population of mice are black, big B, and 50% are recessive, little brown b, then we can know that the percentage of gametes that the female carry for the big B would be 50%, and that the percentage of the gametes in the female for the recessive one would be 50%. And from that, we also know that the percentage of the gametes in the male for the dominant black would also be 50%, as well as the carrying for the recessive allele. So if we use that information and do a Punnett square, so these are the female gametes, big R, little r, and we can also notate that by using P for dominant and Q for recessive. And if we use the male gametes, similar to the female one, big R, little r, also noted by dominant and recessive. So if we do the Punnett square, we know that this big R goes here, this big R goes here to give us a big R gamete. And we can also do something similar with the P variable, and that gives us P square. And if we do that for this one, it would be big R, little r, and this would be P and Q. Does anyone want to tell me what the gamete for this box would be? All right, I'll go ahead and do this one. So it'd be big R, little r, and it would be, oh, great job, guys. Yeah, it'd be big R, little r. So what would this one be? What would we put there? Yes, this would be little r, like you mentioned. You're right that it would be 2p, but that's once we add up both the PQ, but just for that one, it would be P and Q because the P comes from here and the Q comes from here. So it wouldn't be 2PQ yet. Okay, but great job getting all these answers right. And this would be, oops, this would be Q and Q. Okay, and from this, we can see how we get the Hardy-Weinberg equation. So from here, we have P squared, and then when we add up the two PQs, we get the 2PQ in the center, and then we also see that there's one Q square. And this is all the possible types you can have. So you can have the homozygous, dominant, homozygous recessive, and the heterozygous. I'm not sure. I haven't heard anything about extra credit for attending, but I will make sure to write down the emails that you guys have provided us and send it to the biology professors. And I'll make sure that they know you were here. So yeah, just put down your email if you want me to notify the professor. Okay, thank you. So yeah, so the P square is the homozygous dominant in the population. This would be the heterozygous, and this would be the homozygous recessive. Any questions so far? Any confusion? Okay. Okay, so in the next part, we'll be applying the Hardy-Weinberg theorem that we just learned and go through some sample problems. So feel free to work it out as I'm going through it. Put questions in the chat. Okay, so the first question is, according to the Hardy-Weinberg theorem, P plus Q equals 1 and P squared plus 2PQ plus Q squared equals 1. So these are two very important relationships that I would commit to memory. So it's asking, what does each of these formula mean and how are the formulas derived? So first let's look at P plus Q equals 1. So what this is saying is that if you add all the dominant alleles for a gene, you will get 100% of the alleles for that gene. So in other words, it's saying that if you add all the homozygous dominant and the homozygous recessive, dominant, recessive, it should give you 100% of alleles in that gene. And that makes sense because in the Hardy-Weinberg theorem, you're only working with genes that have two alleles. So if you add up all the alleles that you have of both the dominant and recessive, it should add up to all the alleles that you have for that gene in the population. And the next equation, P squared plus 2PQ plus Q squared equals 1. So this is saying that if you combine all the individuals that are homozygous dominant for a gene with all the heterozygous and homozygous recessive individuals for that gene, you have counted or combined all the individuals in the population that carry the gene. So in the first equation, P plus Q equals 1, you're just looking at the presence of the dominant and the recessive alleles, but you don't know if that's appearing as homozygous dominant, homozygous recessive, or a heterozygous, whereas the second equation gives you the heterozygous relationship. Any questions on the two equations that we just went over? Any confusions? Okay, let's go to the second question. So this says, assume a population is in Hardy-Weinberg equilibrium for a given genetic autosomal trait. So autosomal meaning it's not in the um, chromosome determining sex, so it's anything other than that. What proportion of the individual in the population is heterozygous for a gene if the frequency of the recessive allele is 1%? So for Hardy-Weinberg equilibrium, it's really important to look at the key terms because it can be easily forgotten or misinterpreted which variable they're asking for. So during an exam or homework, I usually like to highlight the keywords. So here they're asking for the proportion of individuals in a population that are heterozygous. So from that, we know that we're looking for the 2pq because that's what represents the heterozygous. And it's also giving us the frequency for the recessive allele. So we can assume that so let's just arbitrarily say that D is dominant and little d is the recessive allele. And because we know that all the alleles can either be dominant or recessive, they're giving us the recessive allele here as 1%. So we know this equals 1% or 1/100. So I know this problem didn't give us the number of individuals in the population, and when they don't, to do convenient math, we can assume that the population has 100 individuals. So when they're saying 1%, we know that if the population has 100 individuals, that would be 1 in 100 carry the recessive allele. So then we know, so we can utilize this equation equals 1. So if we know this equals 1/100, then we can put that over there and do 1 minus 110, and we can take the common denominator. So that gives us P equals 99/100. But however, the question is asking what is the heterozygous for that gene. So it's important, again, to read the question more carefully because a lot of times it's easy to just leave off here or leave off here, but the question is really asking for the heterozygous of that gene, which is 2pq. So our q is here, our p is here, so we can do 2 times 1/100 times 99/100. And that should give us 198/10,000. And remember that it asks for what proportion, and earlier we talked about how proportions are usually decimals or fractions. So if the same question had asked for frequency, we would most likely convert that into a percentage. But here, since it asked for proportion, we can just leave it as it is. All right, so the next question is giving us exact numbers. So it's saying that about 1 child in 2500 is born with phenylketonuria, which is an inability to metabolize amino acid phenylalanine. And this is known to be a recessive autosomal trait. So if the population is in Hardy-Weinberg equilibrium for this trait, what is the frequency of the phenylketonuria allele? So again, let's assume that P is the normal allele, and little p is the phenylketonuria allele. And we know that the little p is going to be phenylketonuria allele because the question tells us that it's a recessive autosomal trait. So that's why we made the little p for the phenylketonuria allele. So the frequency of the homozygous recessive allele is going to be it's going to be p squared, which in the Hardy-Weinberg equilibrium would be the little q squared, and that would be 1 in 2500. And we got this information from the first sentence here about one child in 2500 is born with the disease. So we know that our q squared is equal to 1 over 2500, and that can be simplified to 1 over 50. So we cannot leave our answer like this because it's asking for the frequency right here. It's saying what is the frequency of it. So we need to convert the fraction into a percentage, which gives us 2%. So this would be the final answer. And part B is asking what proportion of the population constitutes carriers of phenylketonuria allele. So carriers, and in other words, what proportion is heterozygous? Can anyone tell me what part of the Hardy-Weinberg equilibrium we're solving for? Is it the p square, the 2pq, or the q square that we will be solving for? Yeah, that's exactly right. The 2pq part, it gives us the heterozygous information, and since the question's asking us for that, it'll be the 2pq. So from that, so in the previous problem, we figured out that the q was 1 over 50. So again, we can use p plus q equals 1 to figure out what the p is. And that comes out to be 49 over 50. So if we plug all the variable in, it'll be 2 times 1 over 50 times 49 over 50. And that gives us 998 over 2500. And this proportion will be our final answer because the question did not ask for frequency. Okay, any questions so far with the practice problems that we've been going through? All right, let's look at the next question then. Oh, where did the 49 come from? Are you talking about this 49 over 50 right here that I just underlined? Okay, yeah, just in case other people were confused. So what we did was P plus Q equals 1. And from the previous problem, part A, 3 part A, we got that Q was 1 over 50. So that's P plus 150 equals 1. And if we manipulate the equation, we get this would be 50 over 50 minus 1 over 50. And that gives us 49 over 50. Just in case anyone else was confused by that 49. But good clarifying question there. All right, let's look at question 4. So in a purebred Holstein cattle, about 1 calf in 100 is spotted red rather than black. So it's giving us some important information here, 1 in 100 with the red. And it's saying the trait is autosomal and red is recessive to black. So question A, what is the frequency of the red allele in a population? Okay, can anyone tell me if we're solving for the p square, the 2pq, or the q square in this problem? So it's asking for the frequency of the red alleles, and the question says that the red is recessive to black. So that means we would want to solve for the q square because that gives us the information about recessive alleles. Yeah, great job. It is q square. Okay. So from the question, we know that 1 in 100 have red, so that should equal q square. And it's asking for the frequency of the red allele. So we need to get that into q equals, and that gives us 1 over 10, or 10%, since it's asking for the frequency. All right, let's go to part B. What is the frequency of black homozygous cattle in that population? So again, we can use p squared is equal to 1 minus q squared. And this formula comes from the fact that p plus q equals 1. So what we can do is subtract the q on both sides. And then if we were to square this whole quantity would get squared as well. So that's where we get this relationship here. And this is useful when we want to find the black homozygous cattle in the population. So we learned that the Q from the last one was 1 over 10. So we do 1 minus 1 over 10 squared. And this would turn into 9 over 10 squared. And that gives us 81 over 100. And that is the frequency of the black homozygous cattle in the population, and frequency would get turned into percentage of 81%. So part C is asking what is the frequency of the black heterozygous cattle in that population? And similar to the other problems we've done with heterozygous alleles, we would use the 2PQ, and that would be 2 times 1/10 and 9/10, which comes from here. And the 1/10 is from part A of the worksheet that we did. So that gives us 18/100, or 18%. Yeah, so from this problem, we found the frequency of the red allele in the population. We found the frequency of the black homozygous and the black heterozygous. So using the Hardy-Weinberg equilibrium, we can find the different proportion of these alleles that exist in a population. All right, the next one's a little interesting because we're looking at a sex-linked gene for color blindness. Which, as you guys know, appears differently in male than it does in female because it's X-linked. So let's look at this problem. So it's telling us that the probability of the sex-linked gene for color blindness is 0.09, and the probability of the normal allele is 0.91. This means that the probability of the X chromosome, since it's an X-linked gene, for a color blindness allele is going to be 0.09, and the probability of it carrying the normal allele is 0.91. And these two numbers are coming from the information provided in the previous sentence. So this question A is asking, what is the probability of having colorblind male in the population? So for this question, we need to remember that males only have one X chromosome, whereas women have two. And because colorblindness is a sex-linked gene that's only found on the X chromosome and not on the Y, the male are going to have a 0.09 probability. So this would be the 0.09 probability of having X with colorblind genes. And they're going to have a 0.91 probability of having X with the normal allele. And this is because they're giving us the Q and the P, and because they only have, because male only have one X chromosome, we don't need to square that because that would indicate that there are two alleles that can carry that gene, but for male, there is only one allele that can carry a sex-linked gene. So next, let's look at the probability of a colorblind female. So female have two X chromosomes. So that means that a colorblind female needs to be homozygous recessive for the colorblind allele in order for them to feel the detriments of having colorblindness. So because of that, we would look at the Q square because it's a recessive trait and it needs to be homozygous in a female population. So because of that, we would take the Q probability, which is 0.09, and we would square that to give us the probability of colorblindness in a female population. And these numbers should also make sense because the probability of men having colorblindness is a lot higher than female exhibiting colorblind symptoms, just because females have two X chromosomes. So if one is defective, the other X chromosome masks it or helps with it, whereas male only have one X chromosome. So if the colorblind traits are present, then they don't have another X to help like the female do. So that's why the probability of men having colorblindness is a lot higher than in a female. Any questions with question 5 or any of the previous questions? Okay, let's go to question 6. So the ear-tuft allele in chicken is autosomal and produces feathered skin projections near the ear on each side of the hen. So for this, I would probably highlight ear-tuft allele, autosomal. Yeah, that's probably all I would highlight. And then it says that this gene is dominant. So this is another thing that I would highlight and is lethal in a homozygous state. So this is important because it's essentially telling us that if that allele is present in a homozygous state, then the egg will probably terminate itself and not let it develop into a live organism. So that's going to affect the Hardy-Weinberg proportions a little bit. So that's a very useful information. Yeah, so it's saying, in other words, homozygous dominant embryos do not hatch. So homozygous dominant. So then we're assuming there's a population of 6,000 chickens, 2,000 have no ear tufts, and 4,000 do have ear tufts. And it's asking, what are the frequencies of the normal versus ear tuft allele in the population? So we know this gene is lethal in the homozygous condition. So the homozygotes that are produced are not going to hatch and do not appear in the population. Not produced and do not appear in the population. So we know the population has 4,000 heterozygous tufted chicken and 2,000 homozygous normal chicken. And because we don't know how many eggs did not catch, or how many of them contained homozygous tufted chicken, we first need to calculate the allele frequency by assigning alleles to the existing population. So one way to do that is to find out the allele frequencies for the dominant and the recessive, so the tufted and the normal. So let's make a table. So we have 4,000 tufted, 2,000 normal, and then we're looking for the total frequency. Oh, my bad, sorry, total alleles. And then the allele frequency. All right, so for the tufted one, we have 4,000 tufted, which is given to us in the information above, and it's only going to have one of that because we know that if it's homozygous, so if another one of that is present, we know the egg is going to be terminated. So there's only one 4,000 that we list here. But for the normal one, which is the little t, normal, we know the normal can exist in a homozygous state, so one allele can contain the little t and another allele can also contain the little t. So that gives us 8,000. And the total population, so if we add all that up, it gives us 12,000. So to get the allele frequency, it would be 8,000 over 12,000 or 0.66. And for here, same, there would only be one t, and that would be 4,000 over 12,000 or 0.33. So if these are in Hardy-Weinberg equilibrium, we would expect a ratio of little p equals 1 over third and q equal 2 over 3. And for the frequencies of alleles in an egg, it would be, let's do it another way. So again, can you guys hear me now, or is it still a black screen? Okay, awesome, great. When I cut off last time, was it at the end of question 6 or was it later? Okay, that's good. But everything is recorded, so once the session is done, I will be sending the videos to the professor, and hopefully they'll be putting it up on D2L or on Penji. So yeah, we'll have that section and this section, so it'll probably be 2 different videos. Okay, so any questions about question 6? All right, I'm gonna go to the next question. We're almost at the end, just 2 more questions, and okay, so question 7. How can one determine whether a population is not in Hardy-Weinberg equilibrium, and what factors need to be considered? So, like the whole point, like the second part of this activity was to go through process that helps you know whether a population is going through Hardy-Weinberg equilibrium or not. So some important factors would be to calculate the number of individuals in a population that are homozygous versus heterozygous. So it would be calculate And if you know the frequencies of each genotype, you can also calculate the allele frequency, like we did in the last problem. And with the allele frequency, we can calculate the genotype frequency that would be expected in a population if it were Hardy-Weinberg. And then we can compare these values to the values in the population. So it would be to compare the calculated genotype frequencies with Hardy-Weinberg ratios. So this is ideally how you would determine if something is in a Hardy-Weinberg equilibrium or not, and question 6 is a great example to refer back to. But just know that in real life, this is really difficult to do because if an allele shows dominance, it can be hard to distinguish the homozygous dominant from the heterozygous dominant. So because of that, we usually tend to look at frequencies of the homozygous recessive phenotype in a population. And if that remains relatively constant from one generation to the next, we can use that as evidence to assume that the population is in equilibrium, or I should say Hardy-Weinberg equilibrium. All right, question 8. This will be our last question for today. So it's asking us if it's possible for a population's genotype frequency to change from one generation to the next, but its gene allele frequencies to remain constant. So there are a number of ways that this is possible, but we can go through one example of how it could occur. So if we assume inbreeding has occurred in two populations, let's say that they're a population of mice. So there's two populations of mice and there's inbreeding. So inbreeding between two populations. In one population, the mice will become homozygous, and in the other population, the mice will be homozygous for the recessive trait at a specific locus. And if equal number of these guys migrate to a new location, then the frequency of the A allele is going to be 0.5, and the frequency of the little a allele will be 0.5 as well in the new population. And if we look at all the possible combinations of the offspring, so there can be big A offspring, there can be big A, little a, little a, or another big A, little a. So again, like the Hardy-Weinberg ratio that we saw in the beginning. So if each of these mating and the offspring occur in equal probability, and as a result, there will be 1/4 of a population with big A, little a, and 1/2 with big A, little a, and 1/4 of little a. And because of this ratio, we see that within one generation of the population, it has gone to Hardy-Weinberg equilibrium. So there were two inbreeding mice with big A, little a, and when they inbred, we got 50% of big A, 50% of little a. And then when they mated in a new area, we went to Hardy-Weinberg equilibrium. The offsprings showed Hardy-Weinberg equilibrium for the genotypes. But we see that the the frequency of the allele remained the same, so 0.05, 0.05. So the frequency of the allele stayed the same, but the genotype is in Hardy-Weinberg equilibrium. So from that, we can say that it is possible for the population's genotype frequency to change, but for the allele frequency to remain constant. And this is just one example of it happening, but there's a number of ways that it's possible and in a number of different populations. Okay, so that was the last question on today's worksheet. Any questions so far, or just thoughts or concerns about the overall stream today? Oh, okay, so if they're saying like there's a population of mice, like black mice versus gray mice, Um, yeah, that can get a little confusing. What I usually try to do in that scenario is look for because they should usually give you other information regarding if that color is going to be dominant, recessive, or heterozygous. I believe we went through an example problem. Let's see. Yeah, like here, like for question 6, it's saying that Um, it produces feathered chicken projection, so that's a phenotype, and a lot of the time that can be confusing about like what does that exactly mean? But then they tell you that that gene is dominant and lethal in the homozygous state, so from that you know that the feathered skin, if it's um like big A, since it's saying dominant and homozygous, then you know like that's the genotype that they're referring to. Was that what you were kind of asking about, or did I totally miss the question? Oh, okay, yeah, that type of example. Yeah, usually for that, I just look at other information that's provided because usually they should give you that. And for me, like I love highlighting it. So like in an exam or in a classroom environment, it can be like stressful. It's easy to misread stuff. So highlighting really helps to just glance really quickly at the important information. Okay, well, thank you everyone for coming to the first biology stream that we've ever done. This was something totally new, but I'm so happy that a lot of people showed up, and I'm really excited for the stream next week. So, yeah, yeah, you're welcome. Thank you for coming. Yeah. All right, I'm gonna stop the stream now. All right, have a great day, everyone.